Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, let's discuss few interview questions related to Verilog. And this is part 4 of our Verilog interview question series where we are going to discuss few questions. Like I will be giving you some time. You can basically pause this video after saying this particular question. You can answer it and you can resume for cross verification, right? So without wasting more time, let's start this particular video. Over here, the very first question is what are the difference between for loop unrolling and generate for when operating in Verilog and when would you choose each? So you can pause this video, you can think of the answer, you can resume for cross verification. Yes, I hope you have answered this particular question. Let's see the solution for this. So basically, a for loop is used for memory initializations where you are going to iterate your loop, right? So, for example, if you can simply write down for I is equal to 0, I less than some memory depth, I is equal to I plus 1. You can write it down so that it is going to be unrolled at the elaboration time into a sequential or parallel if it is in combinational always hardware, right? But in the case of your generate for loop, it's kind of a structural elaboration mechanism that instantiates hardware replicas at the compile time. So basically, let's say suppose if you're going to build a 30-bit ripple carry adder, and let's say if you want to have 30 instances of your ripple adders, then you can use generate for loop and you can iterate the instances for 30 number of times. So in that particular case, you can think of using a generate for loop, right? So we can use this generate for loop for replicating module instances, creating parameterized bus structures, conditional module inclusions, and generate for can access genvar index in the instance name. Yeah, so you're basically going to use genvar variable which is being declared inside your generate for loop. Without using it, you cannot use it in generate for loop, right? So this is between the difference between your for loop and generate for loop. Now, so yeah, this is the example for this where we are going to use a simple for loop for some particular thing and generate for loop for creating the different kind of instances. Now, next question is explain how an arithmetic right shift differs from a logical right shift for signed vectors in case of your Verilog, and how do you implement each correctly? So you can think of this particular answer and you can pause this and you can think and you can resume for the cross verification. Yes, I hope you have answered this particular question. Now, in the case of my logical right shift operation, this is how the symbol is going to be looked. This is my logical right shift operator. And if I'm going to use this logical right shift operator, it is going to fill the vacated MS bits with 0. For example, if I'm going to have 1010, and if I'm going to perform logical right shift operation on this particular variable, then my result will be simply 0101. So MSB is filled with 0 regardless of the sign. So it might be a signed bit or it might be an unsigned variable. Regardless of that particular sign, you are going to fill 0 if I'm going to use logical right shift operator. But in the case of my arithmetic right shift operator, the vacant bits, that is my MSB will be preserved. That is nothing but the sign of that particular number. Okay. So let's say suppose if I'm going to have this number again 1010, and let's say if this is declared as a signed variable. So I'm going to use a keyword signed if I'm going to use a data type rich, right? Now what is going to happen if I'm going to perform right shift? Then MSB is preserved and my right shifted result will be 1101. So this is the result of my arithmetic right shift. And over here in Verilog, I'm going to use this operator for performing arithmetic shift. But if the operand is declared as signed only, this is what it is going to happen because reg is an unsigned data type by default. So if you are not going to use this signed keyword, then arithmetic shift right shift operator is also going to act as a normal logical shift operator only. So you should make sure that you are going to use this signed keyword, right? So so an unsigned rich, it is going to behave as a normal logical shift operator. And if I want to force the arithmetic shift, I can use this dollar sign, right? Yes. So this is the difference between your logical right shift operator and arithmetic right shift operator. Now, the next question over here is like, what are the timing hazards introduced by large vector muxes and how do you mitigate them in synthesis? So you can pause this video, think about the answer, and you can resume for the cross verification. Yes, I hope you have answered this particular question. Now, let's see what is the answer. So basically, glitches occur in combinational logic when multiple signal changes at slightly different times, causing transient incorrect values at the output before settling. For example, if I'm going to have a large 32 cross 1 mux on a 32-bit buses, so the hazard arises when multiple select lines and data lines change simultaneously, creating ripple effects through the mux tree. For example, if I'm going to have a particular code like this, assign out is equal to select, depending upon my select, I'm going to decide which particular data should be given to your output. Now, let's say if this select is having some glitches, let's say if this select is equal to 0, your data, if this select is equal to 1, you're going to select this data A, or if it is equal to 1, you're going to select data underscore A, and if it is equal to 0, you're going to select data underscore B, right? Now, let's say due to some glitch in your select line, instead of a constant one, if we are going to get this kind of behavior in my select, then up to here data A was being selected and immediately data B will be selected because your select line has been changed. And again, you're going to get data A and again data B, and again up to from here, you're going to get data A, right? So this is a glitch which is not expected. Data B should not be expected, but due to the glitch in your select line, you're going to get this particular glitch. Now, for this, what we can do is we can basically register the output. That means I can pipeline the mux to prevent glitches from propagating. For example, I can simply use a always at the rate passage of clock, and I can write down this particular code inside my always at the rate passage of clock, so that now this particular multiplexer output is pipelined and it is synchronous to clock. So whatever the glitches we are going to get, that will be removed because we are basically depending upon the clock. This out will be updated only when there is a positive edge of the clock. So whatever the glitches in between we are going to get, that will be mitigated. And next is we can use one hot encoding for selects. That's not a good idea, but we can use this always at the rate passage of clock. And we can also apply static timing analysis to verify setup and hold time margins. And we can also perform retiming and all. But in terms of coding, if you want to observe, this is the first method which we can use, right? Yes. So that's about this particular session, and remaining few more questions we have that we are going to discuss in our upcoming sessions, right? So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.